Hi everyone, my name is Tong Wu. Today I will present our paper Universal Latent Homomorphic Manifold, a framework for closed-domain representation unification. The central question of this work is simple. Segmentic description and row observations are often describe the same underlying reality, but they are not through very different pathways. We ask when these different representations can be unified into a single latent structure in a principled way. Our answer is use homomorphism as mathematical criteria for valid unification. Modern machine learning systems usually learn from observations, pixels, sensor values, time series, or other raw measurements. Human, however, often reason through segmentic descriptions, such as labels, attributes, diagnostic states, or textual descriptions. For example, a face image can be represented as pixels in densities, but it can also be described as segmentic attributes such as smiling, eyeglasses, black hair, or young. These are two views are very different, but they refer to the same object. This raises the main question: can segmentic representation and observation-driven representations convert to a same latent geometry? And if they can, how do we know unification is valid rather than just empirical alignment artifact? So the key idea is valid representation unification should preserve topology. In our framework, each observation or segmentic space is mapped into a latent manifold. We say the mapping is structurally valid when it behaves like a homomorphism. It is continuous, invertible into its image, and preserve neighborhoods. In practical, we use bi-Lipschitz condition as a sufficient structure preservation criteria. The lower bound preserves different points from collapsing to the same latent region. The upper bound prevents nearby points from being torn apart. So homomorphism is not only a mapping tool in ULHM, it is a validity test. It tests us whether two segmentic observation pairs can be meaningfully unified. So this slide shows the overview of universal latent homomorphic manifold framework. During training, the model receives pair segmenting and observation information, and the observation site may contain images, sparse measurements, or sensor inputs. The segmentic site may contain labels, attributes, or descriptions. Both sites are encoded as a shared latent manifold. From these latent manifolds, the methods can be reconstructed observations, align domains, or support downstream reasoning tasks. A key feature is asymmetric. We can use rich segmentic information during training, but at test time, the model can operate from observations alone. The segmentic structure becomes embedded in geometry of the latent space. The universal latent homomorphic manifold objective combines on reconstruction, cross-model consistency, local topology preservation, and optional perceptual quality. The reconstruction losses keep the latent code informative. If the encoder collapses many distinct samples into the same code, the reconstruction becomes poor, so the items helps to maintain injectivity. The consistency losses align with different modulities from the same sample. For example, a sparse image, a complete image, facial attributes should map into nearby regions in the latent manifold. The local topology losses preserves neighborhood relationships. For example, two samples are close in the original manifold. They should remain close after encoding. Together, these items encourage the nerd representation to satisfy homomorphic structure we lead for reliable unification. Training alone, it is not enough. We also verify whether the nerd latent space actually behaves like a uniform or homomorphic manifold. We use a three-level verification protocol. First, global match checks whether the latent space forms a single connected structure and whether different domain distributions overlap. We use Betti number and slice the Wasserstein distance for this. Second, local match checks whether the neighborhoods are preserved. We use trust score to detect collapse and continuity to detect tearing or incoherent local structure. Third, segmentic match check whether paired segmentic and observation samples are synchronized in a latent space using alignment arrow. The important point is universal latent homomorphic does not assume transfer is always valid. It verifies the geometry before relying on it. The first application is sparse recurring with segmentic priors. During training, the model sees the complete image, sparse observation, and segmentic attributes. At testing time, however, it receives only sparse noisy observations. No segmentic annotations are provided during the inference. On Celeb dataset, we test reconstruction with very limited measurements. The model learns the sparse pixels, complete images, and attributes should share a common latent geometry. This allowed a segmentic information nerd during training to guide reconstruction implicitly at deployment. The result shows the ULHM achieves lower mean square error than strong baselines at most sparsity levels. For example, at 10% observation rate under Gaussian noise, universal latent homomorphic manifold methods reaches 0.028 mean square error, better than the best competing algorithms around 0.03. At 15% sparsity, the gap becomes larger and with universal homomorphic latent manifold reaching 0.0247. So this supports ideas verify the latent geometry improved recurring from incomplete observations. The second application is closing domain classifier transfer. Here we test whether a classifier trained on one domain can be applied to another domain without retraining. The example is minutes and the fashion minutes. Two domains looks very different, but they share 10 glass segmentic structure. Universal homomorphic latent methods first learns and verifies universal latent manifold for both domains. And then a classifier is trained only on the source domain and evaluates it at the target domain. For minutes to fashion minutes, universal latent homomorphic achieves 86% accuracy without a target domain classifier training. For fashion minutes to minutes, it reaches 96.9%. It shows when the latent manifold passes the homomorphic verification protocol, decision boundary can transfer across domains more reliable. The third application is transductive zero-shot classification. The encoder and decoder observe from all classes, but the classifier receives labels only for class 0 through 4. Class 5 to 9 are held out from classification supervision. As testing time, classifier is performed in the latent manifold using nearest centroid assignment. The reason this works is that the topology preservation objective encourage efficiently segmentively coherent samples to form separated latent region, even when their label class were not used to train classifier. The strong result is CIF FAR 10, where the universal latent homomorphic maneuver achieves 78.76% accuracy on unseen classes. It is 16% percent point higher than the strongest least baseline. It suggests that preservation latent topology is especially helpful when unseen classes are complex and additional variables. At last, to summarize, the universal latent homomorphic makes three contributions. The first one is proposed homomorphic as a mathematical criteria verifying segmentic and observation unification. Second, it introduces training objectives that encourage by Lipschitz topology preservation latent mapping. Third, it provides practical verification metrics so that we can test whether unification has succeeded before using the representation for recurring transfer and zero-shot reasoning. Closed experiment, the framework enables the sparse recurrent with segmentic priors closed domain transfer without retraining and transductive zero-shot classification through preserved latent geometry. The broader message is representation alignment should not only be measured by distributional similarity. We should also ask whether underlying topology is preserved. In the universal latent homomorphic manifold, homomorphic Lisians provides exact that validated test. Thank you.